Hi everyone, in this video, we will learn monitoring and control of pH during a fermentation. In batch culture, or let's say if a batch fermentation is going on, the pH of an actively growing culture will not remain constant for very long. Any fermentation is going on, each fermentation and the process organism that is used in that fermentation has an optimum pH. And let's say if your fermentation goes on for 7 days and the optimum pH for your organism is 7, the pH 7 should be maintained for the 7-day fermentation period. But the pH of the culture doesn't remain constant for very long. And in most processes, there is a need for the pH measurement and control during the fermentation if maximum yield of a product is to be obtained. Rapid changes in the pH or sudden shifts in the pH can often be reduced by the careful design of media or the fermentation media, particularly the choice of carbon and nitrogen sources, and also some buffers can be incorporated into the media. The pH may be further controlled by addition of appropriate quantities of ammonia or sodium hydroxide if it becomes too acidic, or sulfuric acid if the change is to an alkaline condition. Even if you modify the carbon and nitrogen sources or incorporate buffers, and if there is a pH change during the fermentation, you can control by adding alkali or acid, and you have to ensure that you have to add sterile acid or alkali during the fermentation when there is a pH shift. Normally, the pH drift is only in one direction. Now, how would you monitor the pH of a fermentation or a fermentation broth during the fermentation? pH measurement is routinely carried out using a combined glass reference electrode that will withstand repeated sterilization at temperatures of 121 degrees Celsius and high pressures. Of course, the monitoring of pH would require combined glass reference electrodes, but also the thing is that these electrodes should withstand repeated steam sterilization at high temperatures of 121 degrees Celsius and high pressures, because these electrodes will come in direct contact with the fermentation medium, so they have to be sterilized. And these electrodes may be silver chloride with KCl, that is potassium chloride, or special formulations as an electrolyte. Occasionally, calomel mercury electrodes are used, and the electrode is connected via leads to a pH meter or controller. And I said that these electrodes have to be sterile, and they should withstand repeated steam sterilization at 121 degrees Celsius and high pressures. If we are talking about laboratory fermenters, the pH electrodes along with the fermenters can be autoclaved, and they should withstand the sterilization. But yes, repeated sterilization may gradually change the performance of the electrode. The long culture times associated with animal cell culture growth or continuous culture of any cells makes a withdrawal option highly desirable. Batch fermentation, it's a different thing. But if you are carrying out continuous fermentation, which may go on for 100 days or 3 months, there the withdrawal option is highly desirable, so that the pH electrode can be withdrawn from the fermenter to allow servicing of the electrode or troubleshooting without interrupting the fermentation. But the housing for this option needs to be carefully designed, or those who are designing these fermenters, to ensure that the fermentation does not become contaminated when the electrode is withdrawn, serviced, and then re-sterilized and inserted back into the housing or fermenter. There are control units which may be simple on-off or more complex. Let's see how an on-off control unit works. In an on-off controller, the controller is set to a predetermined pH value. Now, let's say that your fermentation, the optimum pH of your fermentation or your process organism is 7. So during the entire fermentation, that pH has to be maintained. That is a pH 7, which is the optimum pH for your process and for your process organism. So in the on-off controller, the controller is set to a predetermined pH value, which is 7 in this case. Now, what if there is a pH change? Let's say the pH, which should be 7 during the fermentation, is changed to 4 or 5. Okay, it's changed to 4 or 5. So ideally the pH should be 7. It's changed to 4 or 5. What happens next? A signal is sent and the signal actuates a relay, and a pinch valve is opened or a pump is started so that acid or alkali is pumped into the fermenter for a short time. So in this on-off controller, you have already set a predetermined pH value, which is 7 in this example or in this case. But the pH is dropped from the ideal pH, that is from 7 to 4 or 5. So a signal actuates or operates a relay where a pinch valve is open, a pump has started, and the acid or alkali is pumped into the fermenter for a short time. And this is governed by process timers. Okay, this step is governed by process timers, and the acid and alkali cannot be pumped into the fermenter for a long time. Otherwise, it would change the pH drastically. Okay, so in this case, the shift is towards the acidic range, and I have to bring back to 7. So alkali would be added, and as the process is governed by a process timer, the alkali would be added only for 0 to 5 seconds. And after that, the addition cycle is followed by a mixing cycle, which is governed by another process timer, that is 0 to 60 seconds. So for 0 to 5 seconds, you have allowed the alkali to enter the broth. After that, there is a mixing cycle where the alkali is mixed into the fermentation broth for 0 to 60 seconds, during which time no further acid or alkali is added. And at the end of the mixing cycle, another pH reading will indicate whether or not there has been adequate correction of the pH drift. In small volumes, the likelihood of overshoot is minimal. So this video was all about how would you monitor and control the pH in a fermentation, and with the example of on-off controllers.